All right, we are here to finish up the rest of Chapter 10's example problems. So we're going to start with Chapter 10.14, which is calculating the root mean square speed of a gas. So the problem is asking to calculate the root mean square speed of molecules in a sample of N2 gas at 25 degrees Celsius. So we're given the temperature, which we of course know we have to convert into kelvins because for gases you always convert to kelvins. So that's the first step right here. You're going to take your 25 plus 273 and it'll get you 298 kelvins. This equation that they are going to use is equation 10.22, and it's just given to you in the book, so it'd be one that like we would write down and just reference. But the root mean square is going to equal the square root of 3 times R times T divided by the molar mass. So R is our gas constant, which is over here, and it again is going to depend on, they give you all of them in the table because it depends on what our units are. So our first step was to convert into kelvins, which we did. The molar mass, so we're talking about N2, which means you take the 14.01 on the periodic table, multiply by 2, and we're going to get 28 grams per mole. And then they convert it into kilograms for a very specific reason. So taking our 28 grams per mole is going to be the same thing as 28 times 10 to the negative third kilograms per mole. The reason why they convert it into kilograms per mole is because we need to get rid of the joules, and we know that 1 joule is the same as 1 kilogram meter squared per second squared. So these kilograms then had to cancel out, which is why we needed kilograms up here for our molar mass. So our R was 8.314 joules per mole K, but again it needed to be in the kilograms so that we could cancel out our units, and we got 8.314 kilograms meter squared second squared mole K. So then everything will cancel out and be what we need, which is meters per second, because we're looking for a speed. So now all we have to do is plug in our numbers into this equation that we were given up here. So we're going to take 3 times that R, which is the 8.314, times the temperature, which we converted into Kelvin, so 298, divided by that molar mass, which is 28, times 10 to the negative third. So you'll see that moles cancels out, our kilograms cancel out, our kelvins cancel out, and we're going to be left with our units in meters per second, which is again what we want because we're talking about speed. And once you do all those calculations, you get 5.15 times 10 to the second meters per second. All right, so we're gonna go to problem 10.15, which is applying Graham's law. An unknown gas composed of homonuclear diatomic molecules, it fuses at a rate that is 0.355 times the rate at which O2 gas diffuses at the same temperature. Calculate the molar mass of the unknown and identify it. So we are given the equation of Graham's law right here. R1 over R2 equals the square root of M2 over M1. We know that one of them is going to be labeled as X because that's our unknown, and the other one is for oxygen or O2. So you have Rx over RO2 is going to be equal to the square root of the molar mass of O2 over the molar mass of our unknown, or X. So this molar mass at the bottom is essentially what we want to find. So this is like our big X here, our unknown. So we know that Rx is going to be 0.355 times faster than that diffusion of O2, so RO2. So therefore you can say that Rx over RO2 equals 0.355, which will then equal the square root of the molar mass of oxygen, so 32.0 grams per mole, divided by the molar mass of our unknown. So we want to get, because we're solving for the one on the bottom, we want to get rid of our square root first, which means we're going to square each side. So we get 32 divided by mx equals 0.355 squared. So then 0.355 squared is going to equal 0.126. And now you're just solving for this mx at the bottom. So you're going to take 32 divided by the 0.126 to get a total of 254 grams per mole. So the molar mass of our unknown substance is 254 grams. Alrighty. Last one here is going to be example 16, which is using the van der Waals equation. So our van der Waals equation is right here, P equals nRT divided by V minus NB minus N squared A over V squared. So remember, A and B are your van der Waals constants for very specific gas molecules, and you can find those in a table. Unfortunately, my picture is covering it up, so I'll let you know what those numbers are there, or my video, whatever it is covering it up. So I'll tell you what those numbers are when we get there, but those are given to you in a table and they're already found. Okay, so we have 1 mole of an ideal gas is confined to 22.41 liters at 0 degrees Celsius. It would exert a pressure of 1 atmosphere. Use the van der Waals equation in table 10.3, which is found on page 412 of our textbook, to estimate the pressure exerted by 1 mole of Cl2 gas in 22.41 liters at 0 degrees Celsius. So we're given a temperature, we're given a volume, we're given an N, and we're given pressure. So what we want to do is, hang on. Okay, now that we're done getting snacks, we need to find the pressure that Cl2 would exert if there's 1 mole, 22.41 liters at 0 degrees Celsius. So again, we have to convert into kelvins, but thankfully this is so easy because 0 plus 273 is 273. So now all we really need to do is plug it into the equation. So we're going to have P is going to equal our N, which is 1 mole, times our gas constant, which in this case we're in liters, atmospheres, moles, and Kelvin, so it's going to be 0.08206, times our temperature, which is 273, divided by our volume, which is 22.41, minus our moles, so 1, times our B, which for Cl2 is 0.0562. So that's that first part of the equation right here. And remember, this B comes from a table, table 10.3. So I didn't just pull this number completely out of nowhere. It's already given to us. We just have to find it because we're talking about Cl2 and go over to the B column. And then we have to do the second part of the equation, which is minus N squared, so 1 squared, times A for Cl2, which is 6.49. And divided again by our volume squared, which is 22.14 squared. Excuse me, 22.41 squared. So when we do all that, we'll get 1.003 atmospheres minus 0.013 atmospheres for a total of 0.990 atmospheres. There are other practice problems underneath that with the answers, so feel free to practice those on your own because I understand that these equations are not necessarily intuitive and will need some practice in working with.